Welcome, everyone. For today's prep, we're going to start the chain rule section here. I don't know if we're going to actually get to the chain rule part of this because we're gonna be looking at kind of the underlying main idea here, and that is composite functions. So chain rule, just to go back to the name there, is one of our special derivative rules, kind of like product rule and quotient rule that we've been looking at. So chain rule is another one of our advanced differentiation rules. And actually, we've seen this rule before. We haven't called it chain rule, but we've actually seen it before. But I want to go through kind of the setup for it in terms of when do we actually use this. And it has to do with a special type of function which we call a composite function. So when we combine functions algebraically, we're kind of used to like adding terms or subtracting or multiplying or dividing. Composition is kind of a different way of taking two functions and combining them. So this is what we're going to be looking at. We're going to be looking at this idea of composite functions, taking two functions and kind of combining them in a way that's different than our usual operations of addition, subtraction, multiplication, and division. Thought that was the laser pointer. It just stayed around there. All right, so let's look at the definition. A function h is the composition of functions f and g if h of x is equal to f with g of x plugged into it. Sometimes we also there is also this other notation. We don't use this one too much, but maybe you've seen it. And it's this little open circle here. And the way we read this is f composed with function g. But this way is how we actually calculate the composition. So when we look at this, we're taking two functions and we're plugging one inside the other function. So when we do this, there's going to be the outer function, which in this definition is f. So we're going to call this the outer function. And then there's what we're plugging in. So in this case, it's g of x. So we're going to call that the inner function. So composition, you almost want to think of it as like an assembly line. So we start with our input x. So we take our kind of our raw material there, and then we put it on our assembly line. And what happens is it goes through function g. So we'll just kind of make that a box there. goes through function g. And what function g does is it spits out g of x. Okay. So that's function g. That's what function g does. It takes some input x, you plug it into the machine, and then you get out g of x. Well, the idea with a composition is then this keeps moving along on our assembly line, and we take g of x, and now we're going to plug that into function f. So this is going to go into function f. And then this spits out f of g of x. And so this is our final output here for this composition. So you can kind of view this as an entire assembly line where we're starting with x, and then it goes through one machine, and then it goes through another machine, and then you end up with the final result there. Or you can kind of just box all this together and say this is just some function, and what we're doing is we're just going from x to that final output. So that's kind of what function h is doing. Yeah, I guess we'll just see. Yeah. So you can just view this you don't have to see all the inner workings. You can just view this whole thing as just h. Okay. So let's get a little practice. This is all theory. Let's get a little practice with this. So let's try example 1. So we have two functions here, f of x equal to x minus 1 over x plus 1, and g of x equal to x cubed. And we're going to calculate the composition f composed with g of x. So in this setup here, g of x is going to be the thing we do first. So g of x is the inner function. So let's see how we can figure out what the formula for this new function is going to be. We're essentially taking two formulas here, two functions, and we're combining them in a special way. So g of x is the thing we're going to do first. So let's actually plug in what g actually does. Gives us x cubed. So that's the first thing, is we're just replacing what that inner function actually is. So we know what g of x is. It's x cubed. And so now the idea is we want to take x cubed and plug that in to our function f. So in our function f, wherever we see an x, got a few x's there, we're just going to replace those with x cubed. So imagine x cubed here, x cubed here, x cubed here. And when we do that, we get x cubed minus 1 over x cubed plus 1. So all we've done is we've plugged x cubed into the kind of the skeleton here of f of x. So I've changed, wherever I see an x in my formula, I've just changed that, in this case, to x cubed. Okay, so this is f composed with g of x. Now let's change the order around. So in the next one, we're going to make f of x the inner function. So let's start with g of f of x here. And first, let's replace what is actually the formula for f of x. So the formula for f of x is the x minus 1 over x plus 1. And let's, while we're at it, let's clear out these. We're gonna kind of think about it differently now. So that's our formula for f of x. So we can tell that from here. So f of x is that fraction. And now we want to take this fraction. You want to think of that whole thing, and maybe it helps to just kind of imagine a circle around this whole thing. So yeah, there's a lot of parts to this, but you want to think of that as just one specific input, and we're going to plug that into function g. So if we go to function g, wherever we see an x, we're going to replace that with that entire fraction. So instead of this x here, we're going to replace this x with that entire fraction. And instead of this x here, we're going to replace it with that entire fraction. So when we do that, in the first case, well, we get our function name here. And then over here, we get x minus 1 over x plus 1. And then that whole thing gets cubed. So we plug that into the cubed function, that entire fraction. And when we do this, we see that these two formula are actually different. So it's worth mentioning the order actually matters. So usually, if you do g of x first, it does not equal the reverse order if you do like f of x first. So order matters. So usually those two compositions are usually different. All right, let's try something else. So in example 1, what did we do? We had the two pieces and we actually combined them together. Now, a lot of times we're going to have a function and we kind of want to break it apart, and we want to write a function as a composite of two simpler functions. So that's what we're going to do in example 2 here. So let's look at function h of x. So this function, this is a perfectly good function. X raised to the power 5 plus 9x plus 3, and then that whole thing raised to the power 8. So this is a perfectly good formula. But what we can do is we can kind of break it down into simpler functions. So the idea here, when we want to try to imagine how is this thing a composition, we want to think about what is the inner function and what is the outer function. And we'll call the inner function g of x, and we'll call the outer function f of x. All right, so usually a good indication for the inner function is if you see parentheses, usually the inner function is all the stuff that's inside the parentheses. So in this case, yeah, we got a nice set of parentheses there, and we're going to call our inner function all the stuff that's inside of it. So it's going to be this polynomial. So our inner function here is x to the power 5 plus 9x plus 3. So we call it the inner function. It's the thing that happens first, but in this case, you really want to look for what's inside parentheses. It's usually a good indication. All right, so if we're going to make all of this our inner function, what you want to do to figure out the outer function is you want to imagine collapsing all of this stuff that's inside the parentheses, collapse all of that down to just a single variable. So we're going to kind of squish all this down so that we just have raised to the power 8. So when you look at it again, parentheses, the raised to the power 8 is literally outside of the parentheses. So kind of why we're calling it the outer function. All right, so we do have to, our function does have to have a variable. So we're just going to squish all this stuff down and just call it x. So our outer function here is just going to be x raised to the power 8. All right, let's try the next one. So for the next one, we have this function k of x, and it's equal to the square root of 4x squared plus 1. Again, we want to write this as the composition of two simpler functions. So we want to think of what's going to be the inner function and what's going to be the outer function. So the inner function, again, kind of stick with the same names. We'll call it g of x, and we'll call our outer function f of x. So again, we want to kind of think about what's inside any parentheses. Well, we don't have any parentheses here, but we do have the square root, and we see that there's stuff inside the square root function. So we're going to let 4x squared plus 1 be the inner function here. Now, if we wanted to get really fancy, we could rewrite this as 4x squared plus 1 raised to the 1/2 power. And then, bingo, we got parentheses there. So the stuff inside the parentheses is the 4x squared plus 1. All right, so we got our inner function. So what's going to be the outer function? Well, literally the stuff outside the parentheses. So if we want to imagine taking all this stuff inside the parentheses and we're just going to squish it down to just a single variable. So we're going to call all this stuff just x. That's inside there. And then it'll be x raised to the 1/2. Or if we wanted to kind of keep the square root, we could just say square root x. Or if we wanted to, x raised to the 1/2. Either one of those would be fine. All right. So this is going to be a helpful way to think of some more complicated functions, is kind of thinking of what's the inner function, what's the outer function. And usually for the inner function, we're trying to look what's inside the parentheses. Now, where we're going with this is we have a special rule, that derivative rule, that tells us how to differentiate these types of functions. And we call it the chain rule. So the chain rule tells us how to calculate the derivative of a composition, where we have an outer function and an inner function. So we have our outer function f and then our inner function g. And what this derivative rule says, so this isn't like product rule or quotient rule or our sum or difference rules. This is a different way of combining functions. So the derivative rule here is going to be, it's something different. And the way this works is we first differentiate the outer function. So that's going to be our first step. Differentiate the outer function. Then the second step is we keep the inner function exactly the same. And then finally, we're going to multiply by the derivative of the inner function. So we want to think of this kind of chain rule as there's three things happening. So we're trying, again, with the chain rule, we're trying to differentiate a composition where we have an outer function and then we have an inner function that's being plugged in. And you want to think of the chain rule here as like we're kind of going through the different layers of the function. So the first step is we got to break through the outer layer first. We got to differentiate our way through the outer layer. So that's the first step. We got to differentiate the outer function. Then we keep the inner function part exactly the same. So we keep the inner function the same. And then we get to differentiate the inner term. So then we multiply by the derivative of the inner term. So we get inside and start differentiating. And we've seen this before. We've actually seen chain rule. We've seen a special case of the chain rule when we did our general power rule. So in this case, for general power rule, the outer function was raised to the power r, and then the inner function was just some inner function we called g of x. And how this general power rule worked is we first differentiated the outer power function. So what do we do with power functions? Well, we take the exponent, bring it down, put it in front. Then we kept what was inside the parentheses exactly the same. So that was keeping the inner function the same. And then we also subtracted 1 from the exponent, normal power rule stuff. And then we multiplied by the derivative of the stuff that was inside the parentheses. So that's what this is. So what this chain rule does is it kind of generalizes this special power rule if our outer function doesn't necessarily have to be a power function anymore. All right, so we're going to get a little practice with this in class. So we'll see you then. Bye-bye.